As we mentioned at the intro video for this module, with statistical mechanics, it's useful because it allows us to get these sort of average macroscopic quantities like energy, temperature, and pressure by looking at microscopic fluctuating quantities. Okay? And so with statistical mechanics, we get these average values, but we could also look at how these values, the entire distribution of these values, right? How they change over time or how they change over different energy levels. And looking at how they change, or in other words, looking at the fluctuations from the average, is just as important as the average value itself, right? Fluctuations from averages are important for systems that are near their critical point, right? Near critical temperature or critical pressure or critical concentration, because these fluctuations will determine the behavior. And furthermore, fluctuations are especially important for very small systems. Fluctuations are especially important for small systems. And that's because in these very small systems, deviations, or the fluctuations from the average, may have values that are just as large as the average themselves. Okay? And so some applications where this is especially important is in the design of silicon chips, in which you're packing, a large amount of transistors into a very tiny space, right? And so you want to understand how, the size, shape, and functionality of these transistors will deviate as a function of the group of transistors. This is also very important in biology, where a lot of times biological function is just an expression of fluctuations from the average sort of value. Okay? All right, and so in order to develop a framework for quantifying the fluctuations, thermodynamic fluctuations, we're going to turn back to our statistical definitions, or statistical tools, and we're just going to look at the variance. Okay? Where this alpha here is some property, and by definition the variance is the average of alpha squared minus the average of alpha squared. Okay? Alright, and so to show you the utility of this, of looking at the variance of a property, what we'll demonstrate is how a property like constant volume heat capacity is related to energy fluctuations. Okay? Alright, so we know that the total internal energy of a system is equal, or the average internal energy of a system, I should say, is equal to Uj Puj, and the summation of that. So let me put an average here. And we know that the probability is described by this. KBT over the partition function Q. Okay. From thermodynamics, we know that the constant volume heat capacity is just going to be equal to the partial derivative of du dt. So that's going to be this, Uj, which is not a function of temperature, and the partial derivative of the probability, which is a function of temperature. Okay? All right, so if we expand this out, we get Uj. Then if we take the derivative of this with respect to temperature, we get the following. put it in brackets to clean it up. Divided by, or minus, exponential kbt over q dq dt. Okay. All right. Now from here, we know that this is p of j, and this is also p of j. Okay. And so we could further simplify it like this. CV is going to be equal to, we'll pull out the stuff that's not a function of j. So we get uj squared plus pj minus 1 over q dq dt summation j uj pj. Okay. All right. So from here, we can recognize that this summation, by definition, is just uj squared, the average of that. And here, this is just the average of uj, or u. Right? Okay. All right, so we'll write that down. uj squared divided by kbt squared minus average uj. But we still have to deal with all this stuff here, right? And so if we take those derivatives and use the partition function, or at least the dq dt term would look like this. kbt exponential j kbt over q. Okay. Of course, we can recognize that this is just p of j again. And so we have the summation of p of j times u of j. And of course, I'll mark it in red. This again will give us another u of j. Okay? Oh, there's a square here. And so in the end, what we find, if I go to the next page, is that CV is going to be equal to, I'll factor out the kBT squared. The heat capacity is just equal to this. And recognizing that this is the definition of the variance, this tells us that the heat capacity is just equal to the variance of the internal energy divided by kBT squared. Alright? So, here, the variance, which is the direct measure of the fluctuations of the energy in the system, we find that the heat capacity is just directly proportional to it. Okay? So CV is proportional to variance of molecular energy right? Of course, you could do similar analyses for other measurable properties.